In this video, I'm going to be talking about the universal law of gravitation, orbit, and little g. What we're going to do is we're going to solve for three different questions. What is the force of gravity of the sun on the Earth? What is the orbital velocity of the Earth around the sun? And what is the little g value on Earth? So here are some important values that we're going to need to use to solve each of these different problems. So let's go ahead and start out. What is the force of gravity of the sun on the Earth, which is the same force of gravity of the Earth on the sun, because every force has an equal and opposite force. So in order to solve that, we're going to be using Newton's universal law of gravitation, which is the force of gravity equals the constant g times each of the masses over the radius squared, which is just the distance between the center of gravity from the sun to the Earth. So what we're going to do is to find the force of gravity between these two. This one is pretty simple. You just have to be pretty careful about plugging values into your calculator because a lot of them, or pretty much all of them, are in scientific notation. So what I'm going to do is set up all the numbers that we need to plug in for the force of gravity, put them into my calculator, and see what we come up with for that FG. All right, so what I did is I just plugged in all of my values into the formula. We have the constant capital G, which is 6.67 times 10 to the negative 11th. M1 and M2 are each of the masses that we're dealing with in this problem. My first mass is the mass of the Earth, which is written right up here. My second one, my M2, is the mass of the sun. The order doesn't really matter here because you're going to get the same product in your numerator. And then on the bottom, we have the distance from the Earth to the sun. So a lot of times you might see the distance displayed as something like this, 150 million kilometers. And you can see right here, I wrote down 1.5 times 10 to the 11th. So what I did is I wanted to make sure that my units were in meters because those are the standard units for any type of radius or distance. So if you have 150 million kilometers, a million is 6 zeros, so it would start out as 150 times 10 to the 6th. So that's 150 million. And then because I typically just set up each of my numbers that are in scientific notation as in one number, a decimal, and another number, I like to place the decimal in the same spot, but it doesn't really matter that much. So if my decimal is right over here, I slid it over 1, 2, which changes it to 1.5 times 10 to the 8th. And then how it finally turned into 1.5 times 10 to the 11th is because it is in kilometers. So if it's in kilometers, then it's times another 1,000. So that's going to add 3 more to our exponent. And then that would change our final value to 1.5 times 10 to the 11th. All right, so a couple tips is when you plug this in, a lot of what you're doing here is mostly just plugging stuff into a formula and then trying to carefully place it into your calculator. So what I typically do is if I'm putting in a number like 1.5 times 10 to the 11th, the way that I'll plug it into my calculator will be like this. I'll hit 1.5. I'll hit this double E function, and then I'll hit 11. Okay, you don't have to type it in like that. I usually choose to because it's a little bit more simple. It saves me time, and I don't have to raise it to an exponent. So this double E function means times 10 to the blank power. So I hit 1.5, double E, and then 11. And then the way it looks in my calculator is like this, 1.5, and it's just going to show 1 capital E and then 11. Okay, so that's the exact same number. If you like to type it in as 1.5 times 10 and then raise it to 11th power, that's going to be exactly the same thing. Okay, so that's just my preference. So what I typically do is I'm going to wrap everything in parentheses so that my calculator doesn't get confused. And what I usually do is I'll wrap these three numbers in parentheses. I'll press enter so then I have my full numerator. And then I'll hit divided by, and then I'll divide it by 1.5 times 10 to the 11th in parentheses squared. Okay, I don't like to put in everything into my calculator at once. If I can break it into smaller steps, I usually choose to do so. If you do want to plug it in all at once, then you're going to have to wrap your entire numerator in parentheses first, so it knows that this is your numerator and then this is your denominator. Okay, in the end, my force of gravity comes out to 3.52 times 10 to the 22nd newtons. So that is the amount of force of the sun pulling on the earth and the earth pulling on the sun, because every force has an equal and opposite force. Going to our second question, what is the orbital velocity of the Earth around the sun? So if you're doing an orbit problem, typically you are identifying the force of gravity between two objects as the centripetal force. Okay, so for the Earth, it has the force of gravity pointed towards the sun, and then as it revolves around the sun, that force of gravity acts as that center seeking, that centripetal force that makes it move around in a circle. So the Fg equals the centripetal force, and the centripetal force is often written as mv squared over r. Okay, so it works out that I already have my Fg for this problem, so I can go ahead and take this number and slide it in here, and then set that equal to mv squared over r. And then when I do that, I would use the mass of the Earth, because the Earth is the thing that is moving around in a circular type motion. So I'm going to go ahead and plug in all the values for this setup, and then go ahead and solve for my orbital velocity. So my orbital velocity came out to 29,747 meters per second. And what I did for that one is I went ahead and placed my mass of the Earth right here, put the v squared over here because that's my unknown. And then my radius for my circle is going to be the distance between the sun and the Earth, which is that 1.5 times 10 to the 11th. So I went ahead and plugged those in, and what you can do is do some cross multiplying. You can take the 1.5 times 10 to the 11th, flip it up and over here. So you're multiplying the R value by your force over here. You're taking your mass, dropping it underneath, and then dividing it by 5.96 times 10 to the 24th. And then you're finishing it off by square rooting it. So there's 3 algebraic steps there. Okay, now if you hadn't solved for this beforehand, what you can actually do is you can do a little bit of canceling out beforehand. So I'm going to go ahead and set up in this corner over here. If you had gm1 m2 over r squared equals mv squared over r, then if you cross multiply this r up and over, that would cancel out the square. And then if you took this mass of the Earth and then dropped it down below over here, then it would cancel out the mass of the Earth. So then you would have your G value, your M2, which is the mass of the sun, and then a single R equal to V squared. Okay, and if you want to take it one step farther, you can go ahead and square root this and say the square root of gm over r equals v. Okay, so if you hadn't already solved for this force of gravity before, you can do some simplifying beforehand so that you can plug in less numbers to get your solution. Now for the final thing, we're going to solve for a little g value on Earth. So when we use little g, we typically just know that's 9.8 on Earth. So you want to find a little g value of any planet or moon. You can use the same strategy that I'm about to show you right now. So a lot of times we just say that fg is equal to mg, and we always use that g of 9.8 on Earth. Okay, now if we're pretending like we don't know the little g value on Earth, we'll just say that mg equals g m1 m2 over r squared. Okay, so there are a couple masses going on here. So pretend this is the mass of a person. So let's just say this is mp, mass of a person. And actually, let's go ahead and change these subscripts over here and then just say that we have the mass of a person over here, and then they're sitting on the Earth. So this is the mass of the Earth. So the mass of the thing that is on the planet doesn't really matter. That's why if anything is dropped near the surface of the Earth, it falls at negative 9.8 meters per second squared. Okay, so that's actually irrelevant. And then from there, you can solve for your little g value. So my capital G is still the same constant of 6.67 times 10 to the negative 11th. We know our mass of the Earth from earlier. It is right over here. And then the distance, your radius, which is the distance from the center of gravity of the Earth to the person, is actually the radius of the Earth. So if there is a person standing on the Earth, okay, and you're measuring the distance from the center of gravity of the Earth to the person, you can see that's half of the Earth, which is the radius. So the distance you're going to use here is the actual radius of the Earth. So let's go ahead and plug in our values and see what we come up with. All right, so as we already knew, the G value is a 9.8. So again, if you're finding the little G value on Earth or any other planet or moon, what you're going to do is you can typically just drop out the first mass. So whatever the mass of the thing standing on the planet or the moon is irrelevant. So little g basically equals g, which is a constant, the mass of your planet or your moon, and then the distance between the center of gravity of the planetary body and the thing is going to be the radius of that moon or planet. So I took the radius of the Earth and then I squared it because that's part of the formula. And then You multiply these two, divide it by the square of that radius, and then I end up with 9.8 meters per second squared. So as a quick recap, so plugging in stuff to find force of gravity is generally fairly simple, but you have to make sure you're very careful with your parentheses and your exponents. And then when you do an orbit problem, you're typically setting up your Fg equal to your centripetal force. So you have a gmm over r squared equal to mv squared over r. And then depending on your situation, you're going to plug in your known values and then do a little bit of algebra from there. And then when you're finding a little g value, it's going to look something like this, where mg equals gmm over r squared, where the mass of the actual object sitting on the planet or the moon drops out. And then you basically have gm over r squared and work it out from there to get your g value. So I hope that was helpful in helping you solve for various values with the universal law of gravitation, orbit, and little g. Thank you for watching and listening.